Okay, so today we will be covering section 4.2, and it's called What Derivatives Tell Us, which I think is a dumb title, but that's what we've got to work with. Okay, so first of all, there's just some definitions we have to talk about. This section is really definition heavy because it's setting us up for different terms we will be using to describe properties of derivatives. So apologies for the heavy definition, but hopefully a lot of them make sense to you guys. Let's see here. Okay, so first we're going to describe increasing and decreasing functions. These should be relatively intuitive, but I am going to just write out the full definition just so you guys have it. So increasing honestly, okay, I lied to you guys. I've decided that I don't want to write out these definitions, but I'm going to draw pictures and then you'll basically know. This isn't the formal definition. This is how I want you guys to think of things, though. So, a function f of x is increasing if f of x, I'll just say f increases as x increases. So this should make some kind of intuitive sense to you guys. It's just a function with positive slopes. Okay, so that's an example. This is an example. This is an example. It's just the values of f are increasing. So if you've taken statistics, you guys know about increasing and decreasing as far as like positive and negative relations. But these are just some examples. And in that same tone, a function, we'll say g of x, is decreasing if g decreases as x increases. So a picture of that would be something like this. This is a decreasing function. This is a decreasing function. And that's a decreasing function. So that's just some terminology for you guys. I hope that it's kind of obvious that if a function is increasing, like these guys, the slopes are positive, right? We're getting larger. And if a function's decreasing, the slopes are negative. Okay. Also note that if it's only increasing on an interval, say from A to B, then you just say it's increasing on A to B. Let's see here, what else? Okay, so as I said, you guys hopefully noticed that if a function is increasing, it has a positive slope, and if it's decreasing, it has a negative slope. And we know that Calc 2, or whatever we're in, Calc 1 is all about derivatives. So we're going to be able to use a derivative, which is the same as slope of the tangent line, or the instantaneous slope of our function, to determine whether a function's increasing or decreasing on a certain area. I guess this will be, this is cheat sheet information, for sure. It says this is called the test for intervals of increase and decrease, but I'm just going to say what I learned this as, which is the first derivative test. And it basically says that if f is, oh god, is continuous on an interval, we'll say a to b, and differentiable, aka you can take the derivative, on, or rather at, all points in a to b, then we have the following. First one is if the first derivative of x is positive, greater than 0, for all x in a b. So for all of the x values in our interval, if our derivative is positive, we know that it's increasing. If you have a positive slope, you're increasing, is what that's saying. And then 2 is if f prime of x is less than 0. Oh, sorry, I didn't even write the statement for that guy. Let me go back to number 1. If this is true, then f of x is increasing on a to b. And then the second one is just the opposite. If f prime of x is less than 0 for all x in a to b, then f of x is decreasing on that interval. Okay, so let's see here. I want kind of an example. Let's do a cubic function. Yeah, I think that'll be the best for an example. So again, this is cheat sheet information, so you want to make sure you have that down, or rather all of this. I'm going to do an example of this, and then we have a couple more applications that we'll be doing today. So we're going to let f of x equal 2x cubed plus 3x squared plus 1. Determine where f of x is increasing and where f of x is decreasing. Sorry, my throat's a little sore. I went on a run, which apparently was a mistake. Okay, so we have from the first derivative test, it's called the first derivative test, or at least I call it that because you take the first derivative, that if we want to find increasing and decreasing, we can just take the derivative and figure out where it's negative and where it's positive. So I'm going to write things in steps again because I think that's really helpful, especially because I can't really answer your guys' questions as I would in a normal lecture. So step 1 is take the derivative. This is just a polynomial, so hopefully you guys are really comfortable with this. We'll get 6x squared plus 6x, and then 1, the derivative of 1 is just 0. So this is what we end up with. Step 2 is actually solving for the x values that give us 0. So we're going to set our derivative equal to 0 and find all of the x values that satisfy that. Because this is going to tell us if we can find all the zeros, then all we have to determine is what's happening in between those, because it'll be consistent. Because a derivative of equaling 0 means that it's either always been 0 or it had to go from positive to negative. We talked about that yesterday. We had maxes and mins because to go from a positive slope to a negative slope, we had to cross a 0 slope. So we're going to find all those 0 points, and that'll help us tell the intervals on which it's increasing and decreasing. All right, so we have 6x squared plus 6x equaling 0. We can divide everything by 6 to get x squared plus x equaling 0. And we can take out an x to get x times x plus 1 equaling 0. And this yields x equaling 0 and x equaling negative 1 as our possible solutions. Okay, so now for step 3, I always draw a number line. You don't have to if you can picture it in your head, but I know I'm a very visual person and a lot of you guys are visual people, so I highly suggest drawing a number line. If anything, it's satisfying. Okay. And you're going to mark the x's from step 2. Okay, so we had x equals 0 and x equals negative 1. Step 4, which I'm actually going to draw in the same area above on my number line, is to pick a number in each number line interval. And by number line interval, I mean stuff to the left of this guy, stuff between these two, and stuff to the right of this guy. So pick a number in each number line interval and plug in to f prime of x. If it's positive, we have from the first derivative test that f is increasing, and if negative, f is decreasing. Okay? So left of x equals negative 1, I'm just going to choose x equaling negative 2 to plug in. It could be anything. This is arbitrary. You could plug in x equals negative 500, but that'll be more complicated. So I try to stick to the number just to the left or just to the right. Something to make this easy. We have f prime of plugging in our negative 2 is equal to 6 times negative 2 squared plus 6 times negative 2. Negative 2 squared is 4, so this is 6 times 4, which is 24, minus 12. Okay, so when we solve that, it gets us 12, which is positive. And I like to, on my number line, mark what's happening to my slopes, so then I can determine increasing or decreasing later. So I know to the left of x equaling negative 1, I have positive slopes. Let me see. Okay. Now we're going to do between negative 1 and 0. I'm going to choose, God, I do not want this to be this close. Hold on. This was our first substep. This is our second substep. So between x equals -1 and x equals 0, we're going to choose x equals -1/2. Kind of a gross number, but we'll make it work. F prime of -1/2 is equal to 6 times -1/2 squared plus 6 times -1/2. And we're going to get, that yields 6 times 1/4 minus 6/2 is 3. Hopefully you guys can tell just from these fractions that this guy's going to be negative. You don't actually have to solve it out. You just have to know whether it's positive or negative. So we go back up to our graph. We can draw a negative on the interval between -1 and 0. Okay, so we have one more interval to deal with, and that's for the right of x equaling 0. I'm going to choose x equals 1. Again, that's arbitrary, but it's just any number greater than 0, but x equals 1 is really easy to deal with. So I'll plug in f prime of 1 is equal to 6 times 1 squared plus 6 times 1, which is just 6 plus 6, which is 12. Again, positive. So we can draw on our number line a positive. Okay, and so now we can talk about increasing or decreasing. So the function f of x, not f prime of x anymore, looking at our number line, is increasing. I'm going to use a little arrow for increasing, where f prime of x is positive, decreasing, where f prime of x is negative, and increasing, again, where f prime of x is positive. So as our answer to the question I had, we would say f of x is increasing on -∞ to 1, or sorry, -1. We don't actually include -1 in here, so we have a curved bracket here, because at that exact instant it's switching from a positive slope to a negative slope, and we actually know that the function, the derivative is equal to 0 there, so it's neither positive or negative. So we just have a curved bracket on -1. And we have another area where it's increasing, so we use our little union sign. Again, that just means and. And it's increasing from the right of x equals 0. Again, we're not including 0, so we need curved brackets. Or parentheses, that's what they're called. And we're going from 0 to positive infinity. Okay? It's weird saying okay because you guys can't actually answer me. Anyway, and then for our answer, we'll say f of x is decreasing on -1 to 0. Again, not including either of those points. All right, so that is how to deal with that kind of problem. I'm not going to do another example just because that's really long. Hopefully the steps will help you guys. If I get a bunch of emails asking for another example, I can certainly do that. However, this isn't stuff that's going to be on the second exam. It'll be on the third exam. So we'll be doing more of this after the exam next week, Friday. So you guys don't have to worry about it quite yet. All right. Let us move on again. So last time we talked about sorry, they're defining first derivative test as something else. Let me scroll up for a little bit and make sure I didn't lead you astray. I'm going to call this first derivative test part 1. I I guess. And then we'll have a first derivative test part 2. Okay, so I'm going to draw a graph that I'll be referencing for the rest of this lecture, just to give you guys examples of things that can happen. I'm going to try to be relatively detailed with it, so give me a second. I'll have some function y as a function of x. We'll go from here. Oh, hold on, I'm trying to be very accurate with this so you guys can see clearly what's going on, which is not my forte. That's an undefined function. Guys, drawing is challenging. Okay, then we'll have it come down like this and look something like that. Alright, that was awful, but here's A, here's B. Our function is defined on A to B. And I'm just going to draw some slopes and label some points. So first of all, let's talk about maximums and minimums. This is our absolute maximum. This is our absolute minimum. And then we have a bunch of points where our slopes are equal to 0, which last time we said could indicate a possible local maximum or minimum. So I'm just going to draw the points where our slope is 0. We'll call this y prime, just so you guys know, as like a key. And I'm going to increase this so you can see it better. Okay, so here's a point where our slope is instantaneously 0. Here's a point where our slope is instantaneously 0. Here, let me draw that a little bit better. There we go. Here's a point where our slope's instantaneously 0. And here's another point where our slope is instantaneously 0. All right. And then one more thing I want you guys to notice is that right here, we talked about where derivatives aren't defined, and derivatives aren't defined when we have like a point. So right there, y prime is not defined because it's pointy, I guess, is the non-technical way you could say that. All right, so let's just say what's happening here. We have a local maximum here, just like we talked about yesterday, a local minimum here. But I want you guys to focus on what's happening at these 2 points, and also what's happening. Oh, you guys already know that this is an absolute maximum, so that's fine. Sorry, what's happening at this point and this point. So, basically, we can see that the slope is 0 here, but it's not a local maximum or a local minimum. If we're looking right here, on any interval to the to the sides of it, there are both points higher and points lower. Same here. Any interval you make up, including this point, has points higher and points lower. So this isn't an interval. So what are we going to call this, I guess, is really the focus of our next section. Okay, so I am going to define some new terms for you guys, and then I'll kind of explain how it ties into what we just did. Okay, so we'll do concavity first. It sounds disgusting. Hopefully it'll make a little bit more sense. So there are 2 kinds of concavity. First of all, we have to make sure that we're letting f be differentiable. On, let's say, AB. Then we're going to define f as concave up, if the derivative is increasing on A to B. And we'll describe f as concave down if f prime, the derivative, is decreasing on A to B. So a way that can help you guys remember this is, my calculus teacher actually taught it to me. She said up like a cup. So if your function looks like that, it's concave up, and down like a frown. Which seems kind of cheesy, but it actually is pretty helpful if you don't want to have to think extensively about what f prime of x is doing. But just to illustrate for you guys what this is saying and to label some points, we have a frown here, so instinctively that should be concave down. What's happening there is, if I were to draw in a bunch of little slopes, there's a slope, there's a slope, we know we have this slope, there's another slope, there's another slope. My slope first started out as very steeply positive, and then it was still positive, but less so, right? It's not quite as steep, and it flattened out until it was 0, so it went from a positive slope to 0, and then to a negative slope, and it's a somewhat negative slope here, and then it's a very steep negative slope here. So that's what it's saying when f prime, or sorry, right here, f prime is decreasing. My slope is going from more positive to more negative. And then the up like a cup, for example, is here. And that, if I draw in my slopes, just some example slopes, we can see we start with a very negative slope, flatten out to a 0 slope, and then get more positive. So that's where we say concave up, and that's just f increasing on our interval. So up like a cup, down like a frown. It just needs to look like this and like this. There are points where it's kind of weird. For example, on this interval, we know that this is up like a cup, right? But if we were to actually continue with this line, how it looks like it's supposed to go, that would be down like a frown, right? So at some point in here, we switch from being concave up to concave down. And that's what we're going to talk about next, which is inflection points. So that's telling us where we have those switches. So an inflection point, I guess these are kind of cheat sheet informations. They're just definitions though, so we'll be using them as we go. Not so much as like a formula or a theorem. So let's see here. How do I want to say this? X equals C is an inflection point if f changes concavity at C. So an example of that is approximately right there, approximately right here, and that's where we're switching from concave down to concave up. We can also see that that happens right here. We're going from concave down like a frown to concave up like a cup, and right here as well. So hopefully you guys can kind of intuit that those are our points where we had either a non-existent or, oh sorry, this is also an inflection point. Let me draw one more. Right here. And right here, I believe. I think it's also one right here. I think I got them all. I might be wrong. Anyway, the point is that if you have a spot where the slope is equal to 0 or is not defined, but it isn't a local maximum or a minimum, it's an inflection point. So that's what we'll be talking about next. And it kind of finishes off the first derivative test for us. So I'm going to write the first derivative test part 2. And that is basically 3 criterion. So if f prime changes from positive, wow, I can't spell, to negative at x equals c, then we say that f has a local maximum at c. So if we look back up at our graph, that's what's happening here. We had f changing from positive, or sorry, the derivative, so f prime changing from positive to negative at this point here, which is our local maximum. Likewise, if f prime of x changes from negative to positive, at x equals c, then f has a local minimum at x equals c. Okay? And then if f prime of x is either positive on, sorry, my handwriting's getting sloppy, both sides of x equals c, or negative on both sides of x equals c, then f has no local extrema at x equals c. So if you find a critical point, yesterday we talked about, if we recall, a critical point occurs where our derivative is equal to 0. So a critical point can either be a maximum, a minimum, or an inflection point. Okay? So critical points, oh sorry, I guess where f prime of x is equal to 0 or f prime of x does not exist. And so all the points there where it isn't a maximum or a minimum, then it's an inflection point. Okay? So we're going to do one more example and then we're going to call it for today because I don't want to do any more. All right, so using those two terms that we just found and the new first derivative test, let's do the second example. We are going to, let's see here. Sorry guys, my notes are kind of scattered. Okay. Ew, this looks disgusting. I hate examples. That's fine. Okay. So we're going to let f of x equal 3x to the fourth minus 4x to the third minus 6x squared. And we're going to add 12x and 1. I don't know why I said it that way. It's fine. Okay, so I want us to find the intervals of increasing and decreasing like we did last time. And also find the local extrema. Of our function f. So as above, we know that step 1 is just to take the derivative. So we have f prime of x equaling 12 times x to the third minus 12 times x squared. Sorry if I do any quick maths errors. Minus 12. Wow, this has a lot of 12s. Times x plus 12. Alright, that's our derivative. And then step 2 is to find where f prime of x is equal to 0. So we have 12x cubed minus 12x squared minus 12x plus 12 equaling 0. We can divide everything by 12. We get x cubed minus x squared minus x plus 1 equals 0. This is heavily disgusting. I don't think you'd have to do something this terrible on an exam. You could factor this using Symbolab. If you factored it, you'll get x plus 1 times x minus 1 squared equaling 0. You should never have to factor something like that by hand in the real world. So that's good. And we get that this equals 0 at x equals negative 1 and x equals positive 1. Okay, so step 3 is to draw our number line. And label our points. We've got x equaling negative 1 and x equaling 1. Step 4 is to plug in, I'm going to call them middle points. That's not a real term. But just points in between where our inflection points are, or our zeros for our derivative. Okay, so we're going to do x equaling negative 2 for the left of x equals negative 1. That gives us f prime of negative 2, which I'm not going to write out. I don't want to write that out. Oh god, I think I have to. Okay, actually, I think I can do this easier. I'm going to use the factored version, which is 12 times, here, I'll write it on the side here for you guys. F prime of x is equal to 12 times x minus 1 squared times x plus 1. So if I plug in a negative 2, I'm going to have 12 times x, negative 2 minus 1 squared times negative 2 plus 1. To do some quick maths, because I just need to know whether this is positive or negative, I have this is positive. Negative 2 minus 1 is a negative number squared, though, is positive. And then we have negative 2 plus 1 is equal to negative 1, so that's negative. And if we have a positive and a positive times a negative, that overall is negative. So to the left of negative 1, we have a negative for our f prime of x. Our slopes are negative. Okay, in between the other points, we have, let's do x equals 0, between x equals negative 1 and x equals 1. F prime of 0 is going to be 12 times 0 minus 1 squared times 0 plus 1. And that's just negative 1 squared is positive 1. So it's just 12 times 1, which hopefully you guys understand is positive. So we have a positive slope right here. All right, we have one final section to check. So let's do x equals 2 for the right of x equals 1. We have f prime of 2 is equal to 12 times 2 minus 1 squared times 2 plus 1. So this is a positive times a positive times a positive, which is positive. So we have the slope is also positive to the right of positive 1. Okay, so now we just have to use the first derivative test to tell us where our local maximums are. Let's really quick write down where our function is increasing or decreasing. So part of our answer is f of x is increasing on, it's wherever the slopes are positive, so we know that's just everything to the right of negative 1. So negative 1 to positive infinity, not inclusive, curly brackets, or not curly brackets, parentheses. And f of x is decreasing on everything else. So that is from negative infinity to negative 1. Step 4 in this case, or not step 4, we're on step 5, is just to use the first derivative test, part 2, to find local extrema. And we can look up at our graph up here to find the local extrema. So we know from the first derivative test, we can go back and look at it, that our function has a local maximum when we're changing from positive to negative, and a local minimum when we're changing from negative to positive. And if it stays the same, we don't have any local extrema. So we just have to recognize the points where it changes, and we're done. And if we look at our number line, it changes from negative to positive at x equals negative 1, and it doesn't change at all at x equals 1. So we know our only local extrema occurs at x equals negative 1, so we say this is answer part 2, local extrema at x equals negative 1. And we know that our slope is changing from a negative slope, so negative slope, to a positive slope, which gives us a minimum. So we're going to have a local minimum of f at negative 1 is equal to negative 10. Okay, so that would be your answer. Hopefully, let's see here. This is gonna be not ideal. Anyway, hopefully I'm not upside down. Hopefully today's lecture made a little bit more sense, and hopefully the audio works out. I do appreciate those of you who have emailed me issues that you've had, because it helps me kind of understand what's going on. If you have a time conflict with the exam that's going to be on Thursday from 5 to 7, please email me now before I set up the exam so that I can create like an individual circumstance for you guys. Please note I want everyone to be taking the exam at approximately the same time. So if it's a major issue and we have to change your exam multiple days, we'll set you up for a predetermined makeup exam with all the other students who will be missing it. So it's just important for me to figure out when that'll be. Yeah, that's pretty much it. Hope this all makes sense for you guys. Tomorrow we'll be doing a final review for your exam. Thursday's your exam, and we'll move on after that. Alrighty.